I'll start with this title. The solubility of substance is important for controlling the bioavailability (BA) of drugs in the pharmaceutical field. The formulation of a eutectic mixture has been proposed as a technique to increase the aqueous solubility and bioavailability of drugs. Lowering the melting point increases solubility and drug delivery efficiency. Ketoprofen, KTP, a poor solubility drug, is expected to improve BA by mixing with a lidocaine, ADC. The purpose of this study is to trace the formulation mechanism of KTP and ADC eutectic mixture. The experiment used DC and FTIR measurements. First, we created a solid-liquid phase diagram using DC thermograms to analyze the melting process. This figure shows the result of DC measurements of KTP and ADC mixture at various mole fraction. In the thermogram of the mixture, a broad peak with multiple overlapping endothermic peaks was observed. The broad peak is a decrease in the melting point due to formulation of a eutectic mixture. For the assignment and physical interpretation of those peaks, we used 3 Gaussians as basis function to reproduce the measured value. We created a solid-liquid phase diagram with the temperature at the left leg of peak as the melting point. In the solid-liquid phase diagram of the KTP and ADC mixture, minimum points were observed at molar ratio of 1:2 and 2:1. In addition, a constant melting point was observed at 294 Kelvin, which is lower than 304 Kelvin. This figure shows snapshot of KTP and ADC crystals in constant under a polarizing microscope at room temperature. We thought that the ADC melted from the constant interface and the molten ADC wrapped around the KTP crystal indicates a peritectic phenomenon. Peritectic is interpreted as melting at 294 Kelvin in the solid-liquid phase diagram. To examine this in detail, a sample cell was set up on the thermostatic plate and filled with KTP crystals. Then ADC was placed on top of the KTP crystal at various ratio. As a result, the absorbance increased with melting. The obtained spectrum change increases multiple elements and is difficult to analyze. We attempt to separate spectral components using singular value decomposition (SVD). SPT was performed on 801 by 250 matrix dataset to traffic spectral changes. We assigned the spectral changes reflected by the first to fourth components using basic vector psi. In psi2, positive peak was assigned to molten ADC peak and negative peak were assigned to molten KTP. This depends on the formulation and melting of peritectic. Next, we verified by kinetic analysis whether the second component was dependent on the peritectic. If the crystal melting process goes through peritectic, it's considered to be a successive reaction. The principal component vector sigma lambda in SVD indicates the magnitude of spectral change. We attempt a kinetic analysis to see if the amount of change match the successive reaction equation shown below. As a result, sigma 2 lambda 2 was compatible with the successive reaction equation. From this, we were able to find a kinetic explanation from the change in the FTIR spectra and confirm the peritectic phenomenon. Thank you for listening.